Let's complete lines and planes in space. So last time we looked at a line in space, and we found that one line in space requires not one, not two, but three equations as a group just to denote a single line in space. Now, the two ingredients that you needed for that line in space in order to get those parametric equations was a line parallel to, or vector parallel to your line, we'll call it V, and then a point P with coordinates x1, y1, z1. And then if you have those two ingredients, you can put together your parametric equations, okay? Now, I want to say something, just sort of an aside about that, which I think is a good thing to mention now. So let's just say you had some line in space. I'm just going to draw some generic line. I don't know if this is going to be the actual, let's just say you had a line like this. Here's a line L, okay? And let's just say that you had a point P on there. I'm just going to make up some point. Let's say it was 1, 2, 5, just say. And let's say the direction vector V was, and I'm just going to make some numbers up here, -4, 3, -7. Okay, there's your direction vector. Fine. If you have those two pieces of information, what would be the set of parametric equations describing this line? So you're going to have x equals, sorry, trying to write too quickly, x equals y equals z equals. It always starts off like that. And then the coordinates of the point, in this case 1, 2, 5, go first, and then plus, the first component of your direction vector multiplied by t for the x equation, and in the y equation, you'll have 2 plus 3t, that other component, and then 5 plus -7t. T is known as the parameter, and that's kind of why they call these the parametric equations. T isn't always the parameter, but it is very common in just about every calculus textbook you might read. Now, we're going to next week visit something called vector valued functions, where we will also see the letter T, the parameter, come up. And in physics, oftentimes we use this T as time, like T equals 1 second or T equals -5 seconds or whatever, okay? Because we're going to use these parametric equations to model motion. Like an object is moving along, in this case, your straight line. And so let's say you had a little object moving, you know, to the left and right on your line, and time t, the parameter, could help you identify the location of your object at any point in time. So let's say somebody said, hey, what point is your object located on at time, say t equals 2 seconds? Okay, well, you would plug t equals 2 into your parametric equations. And let's see, what would we get? We get 1 minus 8, which is -7 for the x. Here we would get 2 plus 6, which is 8 for the y. And we get 5 plus -14, which is -9. So the object that's moving, if you will, if you're using it to model motion, would be at the position at this point, the position with coordinates -7, -8, -9. Okay, so that's how you could locate another point even on the line if you needed other points on your line. So that's kind of good to know. So that's just a little review of the parametric equations for your line. Now, what we also looked at briefly before we finished off last time was how to find the equation for a plane in space. And we found we also needed 2 ingredients to get that single equation. And we needed a point P naught, I'd call it, on the P naught is Q subscript 0, on the plane itself. And a plane is a surface that goes off in infinity directions. It's a flat surface, infinitely thin. And we needed a vector that's normal, which is code for orthogonal to your plane. And if you had those two pieces of info, you could then come up with the standard equation for the plane, which looks like that. And then if you multiply it all out, make it look prettier, eliminate parentheses, you get the more general equation for a plane, which is ax plus by plus cz equals a constant. Now the a, the b, and the c, those coefficients on the variables x, y, and z, I want you to be aware that those are exactly the components of that normal vector. So it's real easy to cherry pick those off if you need them. And we will. So in the next example we're going to do, which I love, I call it the double whammy kind of problem. And yes, these are the kinds of problems I put on quizzes and exams, double whammy. So why do I call it a double whammy? Because it's going to wham you twice. You need to know parametric equations for lines and everything about that, as well as the concept of an equation for a plane at the same time, just in order to do one problem. You have to have all that information and knowledge. So let's take a look at a double whammy kind of problem. Here's one of them. Let's say somebody wants an equation for a plane. Okay, they want an equation for a plane. So if I draw just a flat plane here, there's my plane. Okay, now they're giving us a point on the plane, which is awfully kind of them. So here we have a point P with coordinates 4, -1, 7 that actually lives on the plane. That's good because remember, the two pieces of info we need are a point and a vector that's normal. So now all we hope for is a vector that's normal. But however, they did not give that to us. The very next piece of info, they're not giving us a normal vector. They're giving us a normal line to the plane. Oh, so if I were to draw a picture, there's going to be this line that pierces through the plane, making a 90-degree angle with the plane. And the parametric equations for that line are given here. X equals 2 minus 5t, y equals 1 plus 3t, z equals -t. Fine. Well, kind of what do we do? How do we get the normal vector? So we need a vector normal to the plane, orthogonal, in order to finish this problem. But here's the news. If you look at the coefficients of the parameter t from the line, that will recreate the direction vector for the line. So we can find a direction vector for the line. And that would be this direction vector, I'll call it v, with components -5, 3, -1. So a vector that's, you can think of the vector being on the line, although it may not be, but it is parallel to the line. There's your vector v. We'll just put it on the line because we can always translate it if they're parallel. So that vector is parallel to our line. The good news, and I hope you can see it from my little diagram, is this direction vector for the line v, we can just use it as our normal vector to the plane. We can just say that's our guy. So the claim is the direction vector for the line, since it is perpendicular to the plane, can be used because it is normal to our plane. Yay! And then we win the game. So we're going to finish out the game in the following way. The standard equation for the plane, I like standard form first, and I'd appreciate it if you do this as a first step on my quizzes and exams. Even if MyLab Math doesn't on the view and example, I want it done my way. Otherwise, you'll lose a point or two for not doing it that way. Okay, that's how I kind of tell if people watch my lectures or not. The people that just don't and they do it the MyLab math way every time. Come on. So you're going to go -5 times parentheses x minus the x coordinate of the point that's on the line, plus 3 parentheses y minus the y coordinate on the line is -1, plus -1 parentheses z minus 7 equals 0. And then just multiply it all the way through if they want the general equation. It does look like they want the general, which means multiply it out. Okay. So I'm just going to do some quick algebra here. -5x plus 20 plus 3y, that's a plus 1. So we're going to have plus 3 plus -z plus 7 equals 0. And then when I rearrange this where all of the variables stay on the left, and then we'll add up all the constant terms. Looks like it's going to add up to 30, but then we'll subtract 30 from both sides. And we're done. Now, let me just tell you one thing, though, and I'm not going to dock you a point for this, but in a lot of textbooks, when you look at the back of the textbook for the solutions to the odd problems, this may not be in the back of the book. And the reason why is because notice how it has a lot of negative signs in it, more than positives. So a lot of times, because, you know, we like positives more than negatives, if they've got more negatives than positives, you can change it up by simply multiplying both sides by a -1, and it looks a little bit more nice. That's all. So we're going to go with that one, 5x minus 3y plus z equals 30. And we're done. To recap this problem, you do have to have knowledge of the parametric equations of a line and how to cherry pick off the direction vector for it. And you have to have sort of the visual capability of seeing that the normal line is in fact a line that would be perpendicular to your plane. So a little bit of both.
Professor, could you explain again how you get the direction vector for the line?
Sure, it's the coefficients of the parameter t. So how do I know that? Let's go back to the theorem where we introduced the parametric equations for the line. So go back a few pages in your notes. And when we introduced those parametric equations for the line in the theorem, I hope that you can see that the direction numbers, those are the components of the direction vector, show up as coefficients, ABC, for the parameter t. Can you see that?
Yeah, I see. Okay, thank you.
So if you need to grab the vector, the direction vector for the line quickly, you just look at the parametric equations for the given line and cherry pick the coefficients of your parameter. Easy peasy. Yep.
Just for clarity on how this plane works, right? So like the normal vector is direction of the plane, and
wait. I got to stop you right there. I apologize. The normal vector is a vector that is perpendicular to the plane.
Yes, that's sort of what I
Not in
meant.
the plane, though.
Yes, but it faces the direction the face of the plane is facing, right?
It points in such a way that it's making a 90-degree angle with the plane. So it could either be pointing straight up or straight down. We don't mind either way, as long as it is orthogonal.
Yeah, I think that's where I'm sort of getting at.
Yeah.
Yeah, and the initial point is like where you move it, right, throughout the axis is.
Well, this point here is a point that's contained in the plane. It lives on the plane.
Okay, I see.
I don't think you're allowed to move it around too much because it's a fixed point that they're giving to you. All right, I'm going to move
Okay.
on. If you have further questions, come to my office hours. Let's do the angle between two intersecting planes. So here is a fact, could be a true false question. Yeah. If you have two distinct planes in space, they're either parallel to each other or they intersect in a line. Those are the only two possibilities. So the picture I have here in this diagram, they are intersecting. Now, remember, planes go on forever and ever. So they're just graphing a portion of this plane because it does go off in infinity directions. And they're graphing a portion of the pink plane here. And so they're looking at this angle here, theta, that we have as an angle between the planes. Let's talk about that angle, the angle between them. So how do you get that angle? Now, it turns out you kind of already know the formula, or you've seen somewhat of the formula before, because what the claim is if you look at the normal vectors to these planes, so the normal vector to the blue plane is this guy here, he's making a 90-degree angle, and a normal vector to the pink plane would be like going like this, but we can move him so he's sort of over here. And then this angle between those two vectors will give us the same angle as the angle between the two planes. Cool, huh? So we use previous knowledge. Last week, we even had this theorem given to us. The angle between two vectors, the cosine of the angle, that is the dot product of the two vectors divided by the product of the magnitude of the two vectors. This is almost the formula that we want for the angle between two planes. Why do I say almost? Well, I'm asking you to look at this diagram a little bit further. If I make the blue plane, sort of continue on its, because it's sort of angled down, and if I had the pink plane kind of keep going flat like this, can you see that there's another angle that we can talk about that's obtuse on the other side? I'll call this angle alpha just to distinguish it from theta. Do you see that this angle is bigger than 90 degrees? We don't want that one. We want the angle between the two planes to be the angle that's less than 90 degrees, or exactly 90 degrees, but this isn't. So to ensure that we get the acute angle, not the obtuse, we want our cosine to be positive. So to make sure our cosine is positive, we put absolute value around the numerator to make sure we get a positive result. So this is the formula to find the angle between two planes, not two vectors, two planes. So that's what we do to make sure the angle is the acute one and not the obtuse. We take the absolute value of the dot product of those two normal vectors. Okay. Now, how do you know if two planes are perpendicular to each other? Well, of course, theta would be 90 degrees, right? But what's another quick way to tell if your theta is going to be 90 degrees? Remember we talked about the dot product? The dot product will equal what?
Rho.
0.
Exactly. That is your guarantee. When you have the dot product of two vectors equal 0, you're guaranteed that you're going to have an angle of 90 degrees between them. Good. Now, how would you know if the two planes are parallel? I'll draw a picture. Here are two parallel planes. They never intersect. Oops. How would you know those two planes are in fact parallel? What would your theta be?
0.
Yes. Or
180.
true, but you would never get the 180 because you're going to take the absolute value of this equation. So this one we won't worry. You'd only for vectors. And another way to tell is if one of your normal vectors to the plane is a scalar multiple of the other normal vector. So that's another quick and dirty way to tell. All right, so let's do an example where two planes are in fact parallel to each other. Oh, not yet. Sorry, that's later. I'm getting confused. No, let's do one that's not. Okay, we're going to find the angle between two planes using this formula right here. Okay, so if we're going to use that formula, we need to find the N1 and we need to find the N2. And this is the part where you use your knowledge of equations of planes. And so from our theorem for equations for planes, remember after you multiplied everything out and you got this general form, the A, the B, the C, the coefficients, if you will, of the variables X, Y, and Z are exactly the components of the normal vector. So when you have that normal vector, it ends up being the coefficients of X, Y, and Z. So if you need to cherry pick, you're going to do it now. So the coefficients of X, Y, and Z for the first plane are 1, -2, 1. So there's the normal vector to the plane. I have it. Quick. And the other plane, the normal vector's components are 2, 3, -2. It's that easy. So now we can use this formula here to get the cosine of the angle, and then we'll use our calculators to take cos inverse. So we're going to go absolute value of the dot product divided by the product of the magnitudes. Okay, absolute value of 1 times 2 plus -2 times 3 plus 1 times -2. And that's going to divide by the product of two square roots here. So the first one is going to have the sum of the squares, 1 squared plus 2 squared plus 1 squared. The other one, 2 squared plus 3 squared plus 2 squared. I'm purposely not doing the negatives because when you square a negative, it's positive. So I'm going to get here, 2 plus -6 plus -2, absolute value of, and down here I'm going to have square root of 6 times square root of 17. And that's going to be 6 over the square root of 6 times 17. So what are we saying? We're saying our cosine of the angle that we want is 6 divided by square root of 102. And so now you're just going to take cos inverse of both sides. And I'd be in degree mode if I were you on your calculator. I'm going to round to the nearest hundredth, which means 2 decimal places because they asked me to. Round to the nearest hundredth of the degree, that's 2 decimal places, 53.55 degrees, approximately. So now let's do a problem that is also a double whammy. Actually, it's a triple whammy. Yeah, you might even think it's quadruple based on all of the knowledge that's needed here. But I love this kind of problem. You'll see it in your homeworks and stuff. This is classic problem. So they want us to find parametric equations for a line. Okay. But they want us to find the parametric equations of the line of intersection of two planes right here. Oh, hang on a minute. There we go. So if you go back to the other diagram, which has a nicer drawing, if you go back to where these planes intersect, can you see that these planes intersect in a line? This line right here is the line of intersection of those two surfaces. So they're basically asking us to find the parametric equations for that line. Now, they're not giving us a point on that line, nor are they giving us a direction vector for that line of intersection. Wait, what? And we need those two pieces of info. Oh man, how are we going to get that? Very carefully. So we do have the two equations for the planes. Okay. And from that, we have their two normal vectors. Okay. So if you look at, this picture here, if I put the two normal vectors where their tails are touching, you got that. So what I need you to imagine now, if we take the cross product of N1 and N2, we will actually get a vector that is orthogonal to both, and it'll be parallel to our line of intersection. And that's the big claim. So the claim is the cross product of N1 and N2 gives a direction vector for this line of intersection. So that's going to take some time to go do the cross product, because as you know, it's not super quick. This is a multi-step problem. And so that's going to get us a direction vector. Good news. But what about a point on this line of intersection? There's infinity points, obviously, and all we need is one, but it has to be on that line. It can't just be a point on this plane or a point on that plane. That's not helpful, because it's a point that actually is on both planes. It's a point that is on the intersection. Now, let me just recreate these two equations here. Let me copy them down for a reason. So if you've already taken linear algebra, which is Math 254, you know how to deal with a linear system with two equations and three unknowns. Okay? So I don't want to sit here and teach you a linear algebra class, although it is exciting. So this particular system with two equations and three unknowns is a very special system, because the constant for both equations is 0, which means this system is what we call homogeneous. And homogeneous systems always have a solution. And the solution is super easy to get. It is 0, 0, 0. And you can even test it, like plug the point 0, 0, 0 back into the first equation. Does it work? Does it satisfy the equation? Plug it into the second equation. Does it make him happy too? So good news, we don't have to do a whole lot of work for this particular time. Now, sometimes you won't get lucky and you won't be given a homogeneous system. So what would you do, like if somebody, like if one of these zeros was like, -5 or something like that? Just say, you would do it in a couple of different ways. The linear people, you know how to do it. You would kind of try to diagonalize your system. I'm going to do it sort of in a cheesy way. So I just want to do this because we'll do it in the next problem. How about if you force one of the variables to be 0? So let's just force it. Force the z to be 0. Okay, now what? Well, then you have a 2 equation, 2 unknown system, because you already kind of killed off the z terms and you only have to worry about x and y terms. Now you can solve for x and y. And this is a little system that you've probably seen in an algebra class. Oh, how do I work it? You could use either substitution method or elimination method. If I multiply both sides of the first equation by -2, both sides, if you will, don't forget both sides, you would get what? -2x plus 4y equals 0. And then add that to the second equation like so. And when you add these two equations together, the x gets eliminated. 4y plus 3y is 7y. 7y equals 0. Fine. Solve this for y. You'll get y is 0 over 7, which is 0. And now you could plug that back into your two equations, two unknowns system, and you can find x. And you'll find that x is 0 also. So the 0.000 is in fact a solution to the system. Yay! And we almost are done. They want the parametric equations for the line. Oh, we almost forgot what we were doing. We got carried away. And we also have to do the cross product. So before so I'm going to have like x equals y equals z equals, and I'm going to have zeros here for the coordinates of the point. But now I have to get what are going to be the direction vector components multiplied by my parameter t. So let's go do that now down here. So my cross product of n1 and n2, I'm going to use my 3 by 3 determinant method, I hat, j hat, k hat along the top row, 1, -2, 1 in the second row, 2, 3, -2 in the third row. Okay? And then 2 by 2 I hat minus 2 by 2 j hat plus 2 by 2 k hat. And then you do a 2 by 2 determinant here, -2 times -2, 4 minus 3 times 1, I hat minus, this is -2 minus 2, j hat, plus 3 minus a minus 4, k hat. Woo! And then I get 1 I hat minus -4 j hat plus 7 k hat. I like writing this in component form. So the components are 1, 4, and 7. So now your final answer to the parametric equations for the line, I'm not even going to write the zeros now because 0 plus something is going to give the something. So the x equation, the x parametric equation will be 1 times t, or just t, 4 times t, and 7 times t. And there is your final answer for the parametric equations for the line of intersection. So this was a multi-step problem. I get it. For example 6, I'll start you off and then let you complete, okay? So if you look at the two planes, there they are, okay. If you find the normal vectors to those planes, cherry pick the coefficients from the variables. So n1 is 1, 2, 1, and the other normal vector to the plane would be a vector with 2, 1, -1 as components. Great. And so then you would use the same sort of strategy that the direction vector for this line of intersection, call it V, would be n1 cross n2. So I'll let you go do that. But then how do you get a point that lives on the line of intersection? Now, these two planes don't give us a homogeneous system. So you're not guaranteed of 0, 0, 0 being that trivial answer anymore. Oh, no. Okay. Oh, I see what I did. Ah, interesting. Pardon me. Went too, I could even go further than that, huh? Let's do that. Okay, so how do you get a point on the line? So you have to solve the system. This is the two equation, 3 unknowns system, which you're guaranteed to have infinity answers. So we're going to find a single answer. We're going to do it kind of cheesy. So you've got, here's the system, x plus 2y plus z equals 5, and 2x plus y minus z equals 7. Okay, there's your two equations, 3 unknowns. We're going to do that cheesy way. Now, if I were teaching you linear algebra, I would never let you use this cheesy way, okay? So if you're taking linear right now, and you do this, I imagine your professor might get pretty mad. So don't tell him I did it. But how about if you just set z equal to 0, just force it, so that the system that you have to solve is x plus 2y equals 5 and 2x plus y equals 7. And then you can get solve this system to get the x and y coordinates. And then you know the z coordinate is going to be 0. So I'll let you get the rest of the coordinates for the point. You already know the z1 is 0 because we forced it. And then once you have your direction vector and your point on your line of intersection, voila, you can get your parametric equations. Okay, so go for it and good luck. Now let's talk about sketching planes in space. This is one of the times I'm going to ask you to sketch in 3D on your handwritten work. And it's going to be easy because it'll be very similar to one of these 3 kinds of problems for sketching planes in space. Okay, and you don't have to be a graphic artist to be able to do it. So if a plane intersects one or more of the coordinate planes, we call that line of intersection the trace of the given plane and the coordinate plane. And when you sketch a plane in space, we find the points of intersection with the coordinate axes, write this down, together with its traces, in the coordinate planes. If that sounds like, oh, I'm still confused, Professor, he wrote that all down, I wrote it down, I have no clue what you just said. You are normal. We'll do some examples and it'll be clear. You're going to find the points of intersection first with X, Y, and Z axes. And then once you put those as dots, you can easily just draw the traces. You don't have to do a lot of work to get the traces. Okay, so we're going to start off sketching this plane. 3x plus 2y plus 4z equals 12. Now remember, planes are infinite surfaces, so we're not really going to sketch an infinity surface. We're just going to sketch a small portion of the plane, but it's going to be a good enough picture where you kind of get the feel for where the plane lies in space. And it's kind of cool. I'm excited for you. So here we go. We're first going to get the x-intercept, the y-intercept, and the z-intercept. So this is the first step. X-intercept, then we'll get the y-intercept, then we'll get the z-intercept, and then we'll graph those 3 points and call it a day. Here we go. The x-intercept. Now you guys know from algebra that an x-intercept has the other coordinates 0. So you force the y and the z coordinates to be 0. Force them, because that's what it means to be a point that lives on the x-axis. So in your plane equation, when you substitute zeros in place of y and z, there you go, you're just left with the equation 3x equals 12. And that gives you x equals 4. What does that mean? The point 400 is a point that lives on your plane. Save that for later. Next up, let's go get the y-intercept of this plane. Okay, y-intercepts happen to have x and z coordinates equal to 0. So we're going to force x and z to be 0. So you'll plug in zeros in place of x and z in your equation for the plane. Oops, not equal to 0, that's equal to 12. And then you'll really just get 2y equals 12, so y equals 6. What does that mean? The point with coordinates 0, 6, 0 is a point that lives on your plane. Save him for later. Finally, you'll get the z-intercept that this plane makes, and you're going to set x and y simultaneously equal to 0. So substitute zeros in place of x and y in your equation for the plane. And then I just end up with 4z equals 12, which is z equals 3. And that tells me that the point 0, 0, 3 is a point on my plane. Good news, I can now sketch my plane. So first, make sure you draw your 3 coordinate axes in the way that I've shown multiple times in lecture. And they have to be in these positions when you do the sketch. The x-axis has to point to the left and a little bit downward. The y-axis has to point to the right and a little bit down. And the z is pointing vertically up. Now you can find these intersection points. So on the x-axis, you can kind of, make little tick marks here and find the location where it's 4 and put a dot. That is the point 4, 0, 0. Yay! And then along the y-axis, 1, 2, 3, 4, 5, 6. Find the 6. There's the point 0, 6, 0. And on the z-axis, 1, 2, 3. There's the point with coordinates 0, 0, 3. Now let's talk about traces. What the heck? Well, the trace that this plane makes as it cuts through the XY coordinate plane, that's when z is 0, is this line. It kind of cuts through the XY coordinate plane there. Ooh. Anytime I do a line on there we go. So that line is the trace that the plane makes as it cuts through the XY coordinate plane. And then this straight line here, I'm connecting these 2 dots, is the trace through the YZ coordinate plane. And finally, this line here connecting the X and Z intercepts is the trace that the plane makes through the XZ coordinate plane. And I'm done. And I hope you can imagine that this triangular region here is a portion of the plane. We're just sketching a portion of it. And we're done. Easy peasy. You don't need a graphic arts degree to do it. Let's do letter B because it's a little bit weird. I have oftentimes when students are new to this topic, they look at this 2x plus z equals 1 and they go, oh, that can't be an equation for a plane. It's missing the y. No, as long as the x and y and z are being raised to the 1 power, it's a linear equation and therefore it represents a plane. All it means, since the y is missing, is that there's no y-intercept. That's one less thing we'll have to worry about then. No y-intercept. Now there will be x and z intercepts, so let's talk about it. How do you get the x-intercept? Well, you set everybody else to 0 except for the x. Well, there's only a z. So you'll set z equals to 0 and I get 2x equals 1. And then I solve for x and I get x equals a half. What does that mean? The point with coordinates 1/2, 0, 0 is a point that lives on this plane. Save it for later. How do I get the z-intercept? No problem. We'll set x equal to 0 in this plane equation. Well, then I'm just left with z equals 1. And we're done, yeah. So then the point with coordinates 0, 0, 1 is going to be a point on this plane. And that's the z-intercept. So if I once again draw my coordinate axes, x, y, and z in all the right locations, and along the x-axis, you only want to go 1/2. So if this were 1, you only want to go halfway there. So I'll put the dot right there at the 1/2. And that's the point with coordinates 1/2, 0, 0 right there. And then z is at the 1 right there. So you have the point 0, 0, 1. Now the trace that this plane makes as it cuts through the XZ coordinate plane is this line right here. Just connect the 2 dots. Now here's a big mistake students make. I'm done. I just drew a plane. What do you think, Mom? Well, big problem. That doesn't look like a plane to me. That just looks like a line in space. I want a plane. That doesn't look like a surface. So here's going to be a little bit tricky part. You have to kind of imagine, remember this plane is parallel to the y-axis. It doesn't touch it. So you have to sort of extrude this line so that it kind of keeps going here. And so a portion of the plane would be that right there. And I hope you can appreciate that it never touches the y-axis because the y-axis is behind it. It's parallel to the y-axis. Does that help? Kind of tough to draw in 3D with this one. There it is. And finally, how do you draw this plane? Y equals 3. Oh no, what happened to the X variable and the Z variable? They went to Vegas, they're gone. But there's no X, there's no Z. That can't be a plane. No, it's a plane. It's just a plane that won't have any X and Z intercepts for this guy. So how do you draw that one? Well, go get the y-intercept. Well, what do you think the y-intercept is going to be for this plane? Any guesses?
It's just gonna be a line.
Well, let's go with the y-intercept first. What do you think the y-intercept is?
It's just
It's
going to be
3.
3, isn't it?
Yes, it's going to be 3. So the point 0, 3, 0 is definitely going to be a point contained in the plane. Okay. So let me draw my axes again. I got my X, my Y, my Z going straight up. Okay, along the Y-axis, go find the 3 and then put a dot there. Now this is kind of weird, so try to go with me on this, okay? That is a point contained in the plane. How do you sketch this plane? Very carefully, because this plane is going to be vertically standing up and it's going to be parallel to the XZ plane. So watch how I draw it. I draw a line that's parallel to the x-axis, and I draw a line that's parallel to the z-axis, and then I kind of extend it out. This is not, no, that's not very parallel. Hold on, hang on, let me make it straighter. I can't draw straight lines this morning. I apologize. Woo! Okay, there we go. That looks better. There it is. So this plane is vertical and it's parallel to the XZ coordinate plane. It's a plane. It's still a flat surface, not a line. It's a plane. And we're done sketching that plane in space. And these are the 3 possibilities. These are all the different types of sketching planes in space. You know, one that has all 3 variables, another one that has 2 out of the 3 because one's missing, and another plane equation that has 2 of the variables missing. It only has 1 left. Okay. I hope that helps. And now let's do distances. So when you're finding distances between points and planes, and then that's going to be the easy one. And then we're going to find the distance between a point and a line, a little bit more tricky, a little bit more involved. But those 2 formulas I need you to know because they will be on quizzes and exams. Okay. And I'm going to go over each one with examples. Now, anytime we talk about distance, it's understood that we're talking about the shortest distance. That's important. Don't lose sight of that. So let's do the easier of the 2. How do you get the distance between a point and a plane? And we're going to derive it in slow motion, and then we'll finally have it, and then we'll use it. And I want you to see where it comes from. Because if you did say lose the formula in the middle of some exam, you could always rederive the formula using your knowledge of vectors and projections. Yeah, you could. It's that easy. So here is a picture of the plane. And the point that we want to find the distance to is this point Q right here. And we want to find the shortest distance. Okay, not just any distance. So the shortest distance, I hope you can appreciate, is when you drop a vertical down from the point Q, and this distance D is our goal. Like, what is the shortest distance between the point Q and the plane? Well, you use some of your knowledge of planes. So first you grab a point P that lives on your plane. Well, how do you do that? We'll show you how to do that. I actually already showed you how. Let's just even look at this letter A. How did we get a point on this plane? We actually got 3 different points. Like, look at how we got the x-intercept. The x-intercept was pretty easy to get. All we did was set y and z simultaneously equal to 0. So it's very easy to quickly grab a point that's contained in your plane. No problem there. So we can grab some point P in our plane. And then the normal vector to the plane. Remember, just cherry pick the coefficients of x, y, and z from your plane equation, and you'll easily get your normal vector. Okay, so what you're going to need to do in this derivation to get this d, remember, don't lose sight of the goal. Eyeballs on the goal. We want that d. You're going to form the vector PQ. We're going to do that. And we're going to project it onto the normal vector. So here's the claim. D, the distance, is the magnitude of the projection of this vector PQ onto the normal vector N. Okay, and you can, and it'll work for any point P on the plane. You just have to grab that first if they don't just hand it to you. So I'm gonna show you the formula in slow motion, okay? So I'm gonna start over here on the left, D equals, and I'm gonna do some stuff, do some stuff, do some stuff, and then we'll finally end up with the actual formula that you will use on any homework, quiz, or exam, okay? So the intermediate steps look like this. I just want you to see where they come from. I could just hand it to you and go, okay, just use this. But I mean, aren't you interested in how it got to be? That's part of math, is like the understanding. Although some people would argue, I just want it to be magical. Just give it to me. It's a magic formula and I'll just accept it works. But if you have more of the understanding, that'll lead to better knowledge for foundation for later. Okay, here we go. It is the magnitude of the projection of PQ onto N. And I'm just using all the notation that we learned with projections. Proj PQ onto N. So I'm going to get this magnitude of, and remember the vector that you're projecting onto shows up more often in the projection formula than the vector that you're projecting. So it's going to be a scalar times a vector. The scalar is going to be the dot product of N and PQ divided by the magnitude of N squared, and then the vector that you're multiplying is N. And we're taking the magnitude of this. When you take the magnitude of what's inside here, the magnitude of a dot product just ends up being the absolute value of a dot product, because a dot product is just a scalar. And then the magnitude of N is just magnitude of N, fine. And then the magnitude of a magnitude squared doesn't change it, it's still magnitude squared. Now reduce this to lowest terms. Do you see anything that can cancel?
Yes, the
Magnitude of N.
Exactly. And what's left? And what's left is your formula that you're going to use when you need to find the distance between a point and a plane. Yay! And we win. There it is. Not too hard, because it just involves a dot product, which are always pretty easy to do, and the denominator is just a magnitude. You guys all know how to find magnitudes. Easy. Now, to quickly obtain a point that lives on your plane, given the equation of a plane, you can find an intercept, and whichever intercept is easy. So an x-intercept, or the y-intercept, or an x-intercept. One of those three. I don't care which one, whichever is your personal favorite. You only need one. Okay?
Professor,
Mm-hmm.
is that an absolute value on the N times?
Yes.
PQ? Okay.
Yes, you're exactly right. That is absolute value.
Okay. Thank you.
Absolute value of the dot product. There's a reason you want distance to be a positive number. And sometimes the dot product is negative. So if it is, be sure and take the absolute value if you're finding distance. Okay, here we go. We have a point and a plane. And we want to find the shortest distance between that point and the plane. So, I'm just going to draw a picture. Here's the plane, dee, 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 and here's the point Q, okay? And we want the shortest distance. Ding, D. If I drop a straight line, vertical line down, connecting the Q to this plane. So what the heck? I need a point that lives on the plane. I don't have that, so I need a P. So let's do that first. So step one, get a point P on this plane. Well, it looks to me like it's going to be pretty easy to get an x-intercept. So let's get an x-intercept because that's a legitimate point on the plane. So let's set y and z simultaneously equal to 0 in this plane equation. And when we do that, we'll have 3x equals 6. And then solving for x, we get x equals 2. So the point 2, 0, 0 is going to serve as our point P. That's a nice point P. We like it. Especially since it has a lot of zeros in it. Makes it easier to work with. I love it. Step 2, form the vector PQ. Okay, well, PQ, terminal minus initial and all that. So I'm going to go 1 minus 2, comma, 5 minus 0, comma, -4 minus 0. Those are the components. So my PQ vector is going to look like what? After I do some arithmetic here, -1, 5, -4. Okay. Step 3, get n, the normal vector to the plane by cherry picking. What do I mean by cherry picking? Well, you're just going to cherry pick the coefficients of the x, y, and z from the plane equation. That's guaranteed to give you components of the normal vector to your plane. Guaranteed, like every time. So your n is going to be what, comma, what, comma, what? Anybody have an idea? Easy peasy.
3 minus 1,
Yeah,
2.
yep, exactly. So keep going here. Step 4, you're ready to put it all together. Get your D. Your D is going to be the absolute value of PQ dot product with n all over the magnitude of n. And you have all the ingredients now. So you're ready to rock and roll. So you're going to have absolute value of -1 times 3 plus 5 times -1 plus -4 times 2. Make sure it's absolute value there. You don't want to get a negative distance. That would be bad. And then the square root of the sum of the squares of our normal vector. Square root of 3 squared plus 1 squared plus 2 squared. And what the heck do I have here? Absolute value -3 plus -5. Oh dear, there's a lot of negatives there. This is not looking good. Plus -8. Ooh. All over the square root of what? 9 plus 1 plus 4. I think that's square root of 14. So I get absolute value of -16 all over square root of 14. And of course, when you take an absolute value, you get positive square root of 16 all over, or positive 16 rather, all over square root of 14. And that's, so that this is the exact answer. If MyMathLab asks for the exact answer, please give that. If they ask you for a decimal, then you can whip out your calculator and give the approximate answer. The decimal answer is approximate, roughly 4.28. So we're going to do this distance again, but in a sort of different context. What if somebody gives you 2 planes and says, hey, these planes are parallel, and then prove it. And since they're parallel, you can get a shortest distance between the 2 planes. Hey, but you told us how to get the distance between a point and a plane. How do you get the distance between a plane and a plane? Well, if you just find a point on one of the planes, you just use your knowledge of finding the distance between a point and a plane when you're finding the distance between a plane and a plane. Really? Can you do that? Yeah, it'll work. So the claim is my handwriting is getting in the way. These two planes are parallel. How can you tell? Like, I don't know, I'm not going to sketch them. What's a quick way to tell if those planes are parallel? We could use something we learned earlier. Yeah,
Yeah, check the angle between the normals.
very good. Yeah. Remember that you can use something we learned about, half an hour ago, whatever, in class. If you find a cosine of the angle between them and you get 0 degrees, that would definitely prove they're parallel. That's one way. That's one way. Surely it will work, but I'm lazy. Is there a quicker way? Let me show you something here. I'm going to write down the normal vector to the first plane by cherry picking the coefficients to become the components of the normal vector. And then the other normal vector, I'll cherry pick his components. Now, what about vectors that are parallel? Remember, we learned that vectors that are parallel have a relationship. They're scalar multiples of each other. Remember that? Doesn't one of these vectors look like it's a scalar multiple of the other?
Yeah, the second one.
Yeah,
Like
doesn't it
two?
look like?
Or factor
Yeah.
2, sorry.
Yeah, doesn't it look like all of the components of N2 are double the components of N1? Doesn't that look like the case? You can check it. Ooh, it works. So, yep. So in other words, we're saying N2 is equal to a scalar multiple of N1, where the C is equal to 2. Bingo. And that's proof enough right there. We have just proven that because the normal vectors are parallel, voila, your planes are guaranteed to be parallel. So there's proof. Okay. So we're done with letter A. Yay. So what does that mean? So the sketch would look like, these planes are parallel. So that means we can, I can't seem to do that. Stop. So I can find the shortest distance between those planes. So what I'm going to do is I'm going to find a point on one of the planes, and it doesn't matter which plane you find the point on. And then I'll find a point Q on the other plane, and then we'll form the vector PQ. So what the heck am I saying? So I'll find a point P here on the first plane. How? How about an x-intercept? Those are always easy peasy to find. So if I set y and z equal to 0 in that first equation, I'll get 3x equals 6, and then solving for x, I get a 2. So P on this first plane will be the point with coordinates 2, 0, 0. So I'm going to find a point Q on the other plane, Q on plane 2. Now we could also find an x-intercept if you like. I am going to say I don't want to. Well, how come? Well, the x-intercept is going to be a fraction, and we can go with it. It'll be -2/3, but I don't like fractions. They're messy. So if you don't mind, I'm going to instead find a point on the second plane that'll be a y-intercept, just because, that's how I roll. I like something pretty. So that means I'm going to set the x and the z coordinates equal to 0 to get my y-intercept. And then when I solve for y, I'll get, y equals 2. Oh, that's kind of nice. So my point Q is 0, 2, 0. And that point is over here on the other plane. Okay, this is a multi-step problem here, folks. Don't worry. Boy, this takes forever and a day, doesn't it? And what we're going to do is we're going to form the vector PQ. So that's next. And then we will use the distance formula between a point and a plane. And we can use either of those normal vectors because they're parallel to each other, so it won't matter. But let's form PQ now. So I'll have a terminal minus initial, that's 0 minus 2, comma 2 minus 0, comma 0 minus 0. Okay, so that PQ has components -2, comma 2, comma 0. Okay, fine. Now what? You ready? Because I'm going to use N1 for my normal vector. It doesn't matter which N that you use since they are in fact parallel, but I'll just pick one. And so I'm going to do the absolute value of the dot product of PQ with the vector N1 and divide by the magnitude of N1. So here we go. Distance, absolute value of, let's see, -2 times 3 plus 2 times -1 plus 0. That's nice. And then divide by the square root of 3 squared plus 1 squared plus 2 squared. Oh my. So in the numerator, we're going to have absolute value of -6 minus 2. Denominator, the square root of 14 again. That's going to give us 8 over square root of 14. That's the exact answer. The approximate answer is 2.14. Okay. So there is the distance between two parallel planes. Cool beans. Okay, now we're going to do the slightly harder formula. This one's harder than the point and a plane distance. We're going to find the distance between a point and a line. Okay, so the distance, I'm just going to give you this and then I'll sort of derive it for you below here. The distance is going to be a cross product magnitude between the cross product of PQ with U, and you're going to divide by the magnitude of U. Now, U doesn't have to be a unit vector. I know sometimes I've used U as denoting a unit vector. It isn't here. U will just be the direction vector for the line. And that's easy to get because you're just going to cherry pick it if they give you parametric equations for the line. And then the point P is a point on the line, which is also very easy to cherry pick. So we're going to do both. Okay, so this is what you're going to use as the shortest distance between a point and a line. So the proof here is, and I'm going to run out of room, so let me pull up a new fresh page so I can do this little proof. So the proof, if you've got a line L, so here's your line, like that. Here's a point Q, all right? You want the shortest distance between the point Q and the line, not just any distance. Some time ago, I had a student who gave me some strange answer on a quiz or exam, I forget. And he found a distance, like I think he found like this kind of like, oh, there is a distance between the point and the line. And I went, but that's not the shortest distance. And they weren't very happy. So if I draw a picture of what I mean, why do I need the shortest distance? Suppose that this is the coastline, and let's say you have a ship out here at sea. You know, when somebody says, what's the distance between the ship to shore? You don't just find any distance. They want the shortest distance, right? That would be the point of interest there. Okay. Shortest distance, we're going to call that D. So you got to get a point on the line somehow. So any point on the line will do. Just find one. It's easy to cherry pick off the equation too. You're going to find the vector PQ. Well, what's that got to do with the distance D? Hold on a minute. You also need a direction vector for the line. And the direction vector is a vector parallel to the line. So you could basically say it's on the line. So here's the vector U. That's the direction vector for the line. Okay, fine. And then if you notice that you sort of have a right triangle here, that's a terrible looking, let's call the angle over here theta. between the vectors u and pq. Using trig, since sine of theta is opposite over hypotenuse, sine of this angle is the opposite side leg, which happens to be the distance that we need, and then the hypotenuse would be the magnitude of this PQ vector, fine. If you solve for D by multiplying both sides by sine theta, you get sine theta times magnitude of PQ. Oh boy, that's weird. Now what? Here's the tricky part of the proof. I'm going to multiply this by 1, but it's going to be a very special version of 1, not just 1, because that isn't going to get me anywhere. So what do I mean by a special version of 1? Well, it's going to be a 1 that's going to do some work for me, not just anything. So what's it going to look like? Well, we're still going to have these other factors, sine theta and PQ. And 1 is going to be the magnitude of the direction vector u divided by itself. That's equal to 1. That'll work for me. Okay, then I want you to look at the numerator of this formula so far. By a previous theorem, when we were studying section 13.4 in one of the properties, this product is the same as the cross product's magnitude. Yep, you can go check it. And I'm done with the formulas proof. There it is. Now, there's an alternate way to find the distance between a point and a line using some projections, but I'm kind of short on time. But if you're interested, come to my office hour today and I'll show it to you. It's kind of cool. So let's go do an example. Here's a point. Here's a line. Find the shortest distance between that point and that line. Okay, now they're giving you the answer, but let's get to it. So first get a point P on the line. That's step 1. And you can cherry pick it from the parametric equations. You cherry pick the terms that aren't multiplying with the parameter t. Remember, that's how you cherry pick the direction vector. So the point P has coordinates -2, and because this y equation doesn't have any constant term, 0, and then 1. So the coordinates of the point P that live on the line are -2, 0, 1. If you don't like that point, you're like, well, I don't like that. Fine. There's always a way to find a point, any point on a line if you're given parametric equations. You know, let t equal something. Like, well, I'm going to let t equal, just pick your favorite number, 1, and plug t equals 1 into those parametric equations. And that will give you another position on your line. Go for it. That can give you another point P if you don't like mine. I just plugged in t equals 0, that's all. So the way I found point P is I plugged in my parameter t equals 0 seconds, got my point on the line. Boom. Now what? Now form the vector PQ. That's step 2. Okay. PQ, and they gave us the point Q that's not on the line. That guy has coordinates 3, -1, 4. So we're going to go terminal minus initial, terminal minus initial, terminal minus initial. Okay, and then do the arithmetic. And the components are 5, -1, 3 for that vector PQ. Fine. Now, you'll notice the formula requires a cross product. Uh-oh, we got some work to do. Yeah. So, well, what do you mean? The formula says we got to go get a cross product and then get the magnitude of the cross product. So the next step is go get this cross product of P. Oh, you know what? Before I get that cross product, sorry, let me do an intermediate step. I got to get the direction vector. Let's get you the direction vector for the line. Let's do that intermediate step. How do we get it? Anybody remember how to cherry pick it off of your parametric equations?
Is it 3, -2, 4?
Yeah, exactly. The coefficients of your parameter t. 3, -2, 4. Bingo. So now what? Well, now I never leave myself enough room to do these problems. I don't know why I don't give myself more room. Okay, now step 4, get PQ cross U. What if I want to get U cross PQ? Is that okay? Yeah, it won't matter because ultimately you're going to get the magnitude. So whether you get PQ cross U or U cross PQ for this distance formula, either one is fine with me. And so I'm going to use our trusty 3x3 determinant method where you put I hat, j hat, k hat in row 1. Put the 5, -1, 3, the components of PQ in row 2, and finally put the components of your direction vector down there below in the last row. And then 2x2 I hat minus 2x2 j hat plus a 2x2 k hat. Oh, I'm always running out of room. You know. What a mess. This is where students make mistakes. I have to confess, a lot of times when I'm in a hurry doing cross products, I make silly mistakes because I get minuses and negatives all messed up, and then it messes up the rest of the problem. So be very careful. I do give partial credit, but it may not be as many points as you're expecting. So slow down. Don't get too doing stuff in your head. Write them out. It might help to write out each and every arithmetic step, just to ensure that you don't choke, because you know how frustrating that is when you make a silly mistake. You know, and I know it's no fun. So let's see, -4 plus 6, I get 2i minus 11j plus -7k hat. Ooh, okay, so 2, -11, -7. All right, there is the cross product. Now you're ready to finish out the problem. Your distance formula is a magnitude divided by a magnitude. Your magnitude in the numerator is going to be the magnitude of the cross product. The magnitude in the denominator is the magnitude of that direction vector for your line. Okay. And we get a square root over a square root. Oh my goodness, I got square root of 4 plus 121 plus 49. Yuck. All over square root of 9 plus 4 plus 16. Yucky. I get square root of 174 over square root of 29. Now, you could leave this because this is the exact answer, and this rarely happens, but for this problem, check this out. This actually reduces big time. So I'm going to use a law of radicals. That's true, as long as the radicand is positive for both radicals. Square root over square root can be rewritten as the square root of a quotient, and it turns out this is a nice number. Really? Yeah, it turns out that 174 is divisible by 29. Really? I know, I would never guess this, okay? Like, I don't do stuff like this in my head. But it turns out it reduces to 6. So final answer, square root of 6. That's the exact answer. The approximate answer is 2.45. And there's your distance between the point and the line. I know, and it took a while. Like, one of these problems does take some time. But if you get kind of well versed at getting stuff and just going through the algorithm, the process isn't too hard. This can be a little tedious. So let's recap. The distance between a point and a line. Step 1, got to get a point on the line. Pretty easy to do. Then you form a vector PQ. Not hard. Then you cherry pick your direction vector of your line. Also easy peasy. Next step, go get a cross product. Well, it takes a little bit of time, but it's not that hard. Step 4, put it all together with your distance formula. You got a magnitude over a magnitude. Voila. Okay. I'm pretty much officially done with this section, but we have a little bit of time. So I'm going to go and take a look at these extra problems. And for those of you that may have come in a little bit late, please let me point out that in my Canvas, that the rest of this lecture, I gave you the filled out lecture notes here in Canvas. It's under week 2, under things to know, lines and planes and space extra. It's just an extra page. I uploaded this file. And so I put in some of these extra things for you. So letter A, I already did a problem exactly like letter A. 3 points on a plane. Know how to do that. That's a classic problem. So I gave you the answers in here too, but so you can check yourself. So let's do like a problem or two that's really kind of weird that you have to think a little bit. It's not exactly what I did in lecture. I gave you the answers though, so I just want you to notice that, okay? So this one I already did in lecture, and this one. How about this one? This one's tricky. How about you want an equation for a plane that contains this point and it's parallel to the YZ plane. Uh-oh. So you remember, to get an equation for a plane, you need 2 pieces of info. A point on the plane, I got it, but you need a vector normal to the plane. Oh. So let me draw the picture of sort of what's happening here. The point 1, 2, 3, I don't know, let's just say it's right here. Here's the point. Fine. Now, we want this plane to be parallel to the YZ plane. Now, the YZ plane is this coordinate plane right here. So our plane is going to be a little bit forward of that. So our plane is going to be parallel to that guy. So it's also, you know, sitting vertical like this, but it contains the point. So what I want you to get, what a mess, huh? What I want you to think is, can you think of an obvious vector that is perpendicular to the YZ coordinate plane? And I'm going to give you a hint by drawing one. All right.
1, 0, 0.
Good. It's I hat. Beautiful. It is a vector that's one of the standard unit vectors. And you can use a multiple of that too if you like. I don't care. It's all going to work out. So this is going to be your normal vector to the plane. Because if it's normal to the YZ plane and our plane is parallel to the YZ plane, this vector is also going to be a normal vector for our plane. Yay! And we win. So you're going to use the standard equation 1, you know, use the components x minus 1 plus 0, y minus 2 plus 0, z minus 3 equals 0. Clean it up, you know, 0 times anything, x minus 1 equals 0, or you could even write it as x equals 1, and we're done. That's an equation for a plane, people. X equals 1. Well, what happened to the y and the z? Well, you know, they're gone. So let's look at letter D, and then I'll look at one for the lines, and then we'll call it. This one's a little bit tricky, but I kind of love it. Tricky because they're giving my unfavorite symmetric equations for lines. Yucky. Well, you know. So let's just get the direction vector for these lines. So the direction vector for line number 1, that's this first guy here. If you look at the symmetric equations, the denominators of these fractions, even though you don't see all 3 fractions, the denominators are where you cherry pick your components for your direction vector. So for number 2, the direction vector for line number 2, we'll call it V2, has components -3, 4, -1. Well, how's that going to help us? Well, hang on a minute. Let me draw a picture of what's happening. Here's your plane that you want to find the equation for. Fine. There's 2 lines that are contained in the plane. So I'm just going to draw these 2 lines. Here's line 1, you know, whatever. Here's line 2. Okay, fine. My claim is that if you take the cross product of a direction vector for line 1 and line 2, it will give you a normal vector to the plane. Yeah, true. So I'll go let you do that because you know how to do cross products. And then you just need to find a point on your plane. And you can use either of those lines to do it. And I claim that if I just use what's sitting next to these things right here, 1, 2, 1, that will be a point. But you can also use 1, 4, 0, whichever point you want. So I'll just use 2, 1, 2, and there's a point on your plane because it's on one of the lines, and then go and finish off the problem because you now have the 2 ingredients that you need to get the equation for the plane. That one's involved though, okay? Here's some other ones that are harder. Taking a look at now finding parametric equations for lines, okay? So I'll let you look at some of these. Let me get one that's kind of hard. I kind of like this one. So they're giving you 2 other lines, okay? And you want your line to be perpendicular to those 2 lines. So here's line 1, here's line 2. You want your line 3 to be perpendicular to both of those lines, like this. Okay, so the claim is if you get line 1's direction vector, and then you get line 2's direction vector, the cross product of the direction vectors for line 1 and line 2 will give you the direction vector for our line. And then you can use the point that they gave you, because that's a point contained in our line, and you'll have all the information that you need to come up with the parametric equations for that line. Okay, so go look these up and go read them first before you start doing homework. I would recommend reading the lecture notes over more than once because this is a very juicy section. But we're done. Congratulations.